Newton's third law states that every force has an equal and opposite reaction force. Equal and opposite reaction force. To understand this, we first have to go over how we represent forces on an object. To do that, we draw what's called a free body diagram, where we isolate the object and draw all forces acting on it from the center of mass. So some of the forces that we're going to be dealing with, for example, are going to be the force of gravity, F sub g. An example of that would be like if I had the Earth and the Moon. Well, there's a force of gravity holding these two things together. So I can draw a force here on the Earth towards the Moon and a force on the Moon towards the Earth. These are both forces of gravity. Another example could be a box just sitting on a surface. There is going to be a force of gravity pulling it towards the Earth, or holding it here like this. Another common force that we're going to be dealing with is the normal force. And this is the force applied from any surface. And this force will always be perpendicular to that surface, because, the reason why it's called the normal force is because the word normal means perpendicular. So in this case, this box is sitting on this surface here, and that surface is going to apply a force in this direction. Another example of normal force could be an object sitting on an incline like this. The surface is at an angle that the box is sitting on, and so the normal force is going to be in this direction. If I trace this down to the surface, I should see that it's perpendicular. Same here, if I trace this down to the surface, I should see that the force is perpendicular. And next force we can talk about is the applied force. So F sub A, if somebody is pushing or pulling on something, we can say that it is an applied force by the person. I can draw an example here of a person pushing with their hands. So really this is actually a normal force to the right, but just to make things simpler early on, we can just call this an applied force, because this is really an interaction between two surfaces, and therefore it should be a normal force. Next, we can talk about the force of friction. This is another force that is applied by a surface, but unlike the normal force, the force of friction will always be parallel to the surface. So for example, if this surface here was frictionless, then I wouldn't draw a force of friction, obviously. But if there was friction on this surface between the box and the ground, then in this case, the force of friction is going to be pointing in this direction. Label F sub F. For this box on the inclined plane, normally it would just accelerate downwards. I didn't draw the force of gravity for it, but here it is. So if these were the only two forces, it would slide down the incline. But if it's sitting there, it means that there must be a force of friction holding it up here. And I guess another example of a force could be the tension force, F sub T. This is the force applied when you have it's a pulling force by a rope or a string. So I can draw a box here, suspended by a string from the ceiling. And of course, it's going to have a force of gravity. But this time, instead of a normal force balancing out that force of gravity, it will be a force of tension in that rope. And there are many other forces, and we'll probably learn some more as we go along. I think this is sufficient for now. There are rules for drawing free body diagrams. Or I should say like steps. And I would say that the first step that you should do is to draw the center of mass. So for all of these, I'm drawing the forces from these points here, which are the centers of mass of the objects. And step 2, it would be to just draw forces from the center of mass, which I'll abbreviate as COM, center of mass. So notice here how I drew the normal force from the center pointing outwards. I wouldn't draw it like this, as if there's something pushing up the box from below. Not that that's inherently wrong, it's just this is the way we're going to be drawing forces from the center of mass pointing away from the object, pointing away from the center of mass. And there will be more details here on how we can make drawing free body diagrams easier, but I'd say stick to these 2 steps for now. So now we can go back, now before we go back, another way to represent forces on a free body diagram is, instead of stating the type of force, like here, the applied force, normal force, or force of friction, we can label forces as the force of the 2 objects that are interacting. So for example, the force of gravity can instead be labeled as the force of something applying a force on something else. Let me get rid of this. For this applied force, I can label it as the force of something on something else. Yeah, let's do all of these. This normal force is the force of something on something else. And then the last one we have would be the force of friction. Let me label this better. This would be the force of one object on another. So let's fill these all in. For the applied force here, it's the force of this person acting on the box. So I would label it as person on box. For the force of gravity, there's something pulling down on this box, and that would be the earth. Earth on box. The normal force, there's something pushing up on the box, and that would be the ground, or the surface. And for the force of friction, that's again the ground on the box. One thing to emphasize here is that, notice, because all these forces are drawn on the box, they should all say on box, on box, on box, on box. Okay, so I think with this, we're now ready to have a better understanding of the third law. So we said that every force has an equal and opposite reaction force. And I'm going to add that there are going to be 3 things that will always be true about these equal and opposite forces. Let's be very explicit here. The first thing to note is that the 2 forces will always be equal in magnitude. The 2 forces will always be opposite in direction. And the 2 forces will always appear on different objects. Different objects. So let's do an example of, third law pairs. Every force has an equal and opposite reaction force. So this time I'm going to draw, let's draw a surface here. And we have a box like before. And we're going to have that person pushing on this box. So they have their hands here. And we're going to say that this box, let's make sure that the box is stationary, it's not moving. So all the forces should balance out. We have a net force of 0. I'm going to draw the forces on the box first. Actually, to make this maybe a bit clearer, let's separate these 2 things. I'm going to draw the forces for the box over here. I think it'll be neater. And we'll draw the forces on the person over here. Okay, so both of them will have a force of gravity pushing down on them. And we're going to label them as well as the interacting objects, force of one thing on another. They will both have normal forces from the surface. Okay, now this person is pushing the box to the right, so there is going to be an applied force here. And that is going to be the force of one thing on another. And if this thing is going to be stationary, that means there must be friction between the box and the ground. And for this person to be able to apply a force on the box, there should also be friction here. So the fourth force on the box is going to be a force of friction this way. So force of friction, the force of something on something else. Let's show that these are two separate diagrams. Okay, and so for the person, if they are pushing the box to the right, the box is going to be applying a force on them to the left like this. So we called it here an applied force, so I'll call it an applied force. But again, we know that this is a normal force. Force of something on something else. And then the last force on the person, if there was an unbalanced force in the horizontal direction on this person, it would mean that they're accelerating to the left. So that can't be true, because these two things are going to be stationary. So there must be another force this way on the person, and that is the force of friction, the ground pushing him to the right. So there's a force of friction here, the force of something on something else. Now, based on what I said before, every force has an equal and opposite reaction force. The two forces described here are going to be what's called a third law pair, meaning Newton's third law of motion. Those third law pair forces should be equal in magnitude, opposite in direction, and appear on different objects. A common mistake would be to say that, for example, this normal force and this force of gravity are a third law pair. They are equal in magnitude, they are opposite in direction, but we'll see why these are not a third law pair. Well, one thing is that they don't appear on different objects. So let's go ahead and label in all these objects. So on the box, there's something pushing the box to the right here. That will be the force of the person on the box. The normal force is the force of the ground on the box. The friction is again the ground pushing on the box to the left. And the force of gravity is the earth pushing on the box downward, or pulling the box downward. For the person, gravity is also earth on person. The force of friction is ground on person. The normal force is also the ground pushing up on the person. And this last force to the left is, you can see here that the box is the only thing that can push the person to the left. So this is the force of the box on the person. Labeling the forces in this way makes it very easy to identify third law pairs, because there is only one third law pair in all 8 of these forces. And that is the force of the person on box. This is a third law pair with the force of the box on person. And the way to identify it is just by taking these two names here, the two interacting objects, and swapping them. So if I have force of box on person, the third law pair to it must be the force of the person on the box. So that is here. So we can check now for this common mistake, normal force and gravity, and we can see why those are not third law pairs. If I take the words ground and box and flip them, we don't get earth and box. Okay, so we identified a third law pair. So all those other forces based on the third law should also have equal and opposite forces somewhere else. They should have third law pairs. So for example, what is the third law pair to the force of gravity acting on the person? Well, I have to just look at these two words, earth on person. If I swap them, then it will be the force of something on something else. It's going to be the force of the person person on Earth. So if we zoom out and draw the Earth down here, and that person is sitting on the Earth up here, we know that the Earth is pulling down on this person, and so that person is also pulling up on the Earth with an equal and opposite force. That seems kind of strange. How can the person be pulling up on the Earth? But it's true. The person is applying an equal and opposite force on the Earth. The resulting acceleration of the Earth will be very minimal because the Earth is so massive. But that is still true. So force of person on Earth is this force here. Force of Earth on person is this force here. So that's an example of third law pairs. Let's do one more example of third law pairs. Let's say there's a ball here. Yeah, let's do a bowling ball again. And you have a person that runs along and they kick the bowling ball. So they are going to apply a force in that direction. Let's call it an applied force. It's the force of one object on another. Well, then there must be a force on this person's foot in this direction by the bowling ball. It's the force of something on something else. What do we label these as? Well, the force on the bowling ball is the force of the person on ball, and the force on the person's foot is the force of the ball on person. This is an example. This is another example of third law pairs. So an example of Newton's third law.